Hello, and welcome to our fourth lecture in the Jabrah Reinforcement Learning series. In this lecture, we're going to go through our first reinforcement learning algorithm known as policy iteration. Now, understanding this algorithm is going to be really important because this algorithm is the foundation of most of the other algorithms that we're going to look at in the future lectures. So, the generalized version of this algorithm actually shows how most of these other algorithms work, and it's important that you fully understand how this one works. So since this algorithm is the foundation of what we're going to go through in the future, I've decided to split it into 3 lectures. So we won't just cover this algorithm in this lecture, but the next 2 lectures as well. So what's important to know about this algorithm is that we split it into 2. What is known as policy evaluation, rather prediction, and policy improvement, what we know as control. So this lecture is actually going to be focusing on this, the policy evaluation. The next lecture, so this is for the next lecture. The next lecture will be focusing on policy improvement or control. And finally, the lecture after that will kind of combine these two to get our policy iteration algorithm. And we'll even go through the generalized policy iteration concepts behind understanding how reinforcement learning algorithms work. Right. So let's start with policy evaluation. Now we need to do this with an example to make it easier for you. And if you remember from our very first lecture, we say that our ongoing example would be this one here. So if you remember how this was working, we have this kid who stole money from his parents. So what this kid is trying to do is navigate this maze and trying to reach where we've got the KFC, where you can go buy KFC with the money he stole. But he needs to avoid getting caught, because if he gets caught, he gets a beating, essentially. So all these areas where there's sticks, right, all these states, actually, these are the areas where the kid will get caught and the game is over, or whatever, the scenario is over. But if he reaches the KFC, he achieves his goal, and so forth. So if you remember, we need to go through some of the things like, what is a state in this scenario? Well, the state is essentially where the kid is at, right? So if he starts at this point, we call this, let me use a different color for this. Okay, so we call this S0, right? That's the, let's say, the initial state the kid can be in. And at time step 1, the kid can either be here or he can be there. So let's just give this kind of like a very generic descriptions: A, B, C, D, let's say E, F, G, H, and so forth. So all these letters, so the state space comprises of like S0, which we call the starting state, and then we've got A, we've got B, and so forth, right? This is actually what our states are in this simple environment. And what are the actions that the kid can take, right? So what are the actions? Let's look into that. What are the actions that the kid can take in the states? So essentially, the actions he can take is move right, move to the left, move up, and move down, right? That's how he navigates this maze. These are the possible actions that this kid can take in this kind of scenario that we've described here. So now that we know what the state are, what the actions are, the next thing we need to know is what is our goal, right? So from the last lecture when we looked at goals and rewards, if you remember, the goal was to maximize the return, right? So think for a second, like, what had we defined the return as? So essentially the return is the summation of all possible rewards that the kid will get as he's going through this maze. So let's assume we know the dynamics of this environment, right? We're gonna keep it really simple for this case. So every single time this kid moves from one state to another, he moves either there or he moves there, depending. So every time he moves, he gets a reward of 0, right? Nothing happens. But if the kids end up in this state where there's a stick, if he ends up in a state, right, where there's a stick, so this is if he moves, sorry, let me fix that. So this is the reward, sorry. It ends up where there's a stick, then he gets a reward of say -5, and if he reaches his KFC goal, he gets a reward of +10, right? So the idea is to maximize the reward, and to maximize the reward, you just need to find the series of actions that will lead you to this state, right, where you've got your KFC. So that's how we define our rewards, like this. So right now, it's not important for you to really, what's important actually is for you to just know that, okay, every movement you get no reward. If you reach this, where there's a stick, you get a negative reward. If you reach here, you get a positive reward. That's essentially what we're showing here. And we are showing what the state is, what the actions are, and now what is our goal. Our goal is to maximize the reward, right? So the goal is to maximize, say, the accumulated rewards. So what this means is, imagine like we had a different version of this problem. Here we defined our move as 0, but maybe we might define our move as -1. So that means the kid has to find the fastest way to actually reach this goal, so that he doesn't lose a lot of points for every movement that he makes, right? So depending on the kind of problem you want to solve, maybe you define the reward as 0 because you don't care about the amount of time it takes to reach the KFC. He just wants to reach the point. Or you define it as -1, where you go like, oh, okay, I need to get there as fast as possible. So your reward definition is actually what's going to affect how you actually navigate through this environment. Right? So our goal is to maximize the long-term cumulative rewards, right? This was essentially our goal, or rather to maximize what we call the return, GT, which is equal to, if you remember from our previous lecture, RT plus 1 plus gamma RT plus 2 plus gamma squared RT plus 3. Let me write this more clearly. Gamma squared RT plus 3, and so forth, right? This is how we had returned. This is what we actually want to maximize the return. So we have this kind of definition, okay? You have a basic understanding of this environment. To reiterate, you are in the state, and these are the possible states you could end up in, and these are the actions you can take, and this is the goal, and this is the return, and these are the rewards you can get. So here what you're just supposed to understand, don't focus on this example particularly, but just get the idea of whatever problem you're trying to solve. You are in a certain state, you need to take an action, and each action will lead you to another state with a certain probability, which you should know if you're following our previous videos. And the goal is to maximize the long-term cumulative rewards, right? So now that we've described the scenario, the first thing we need to actually define is what we call the value function, right? So let's move on to the value function, right? So what is this value function, right? We define it as v of s, right? Where s is a state. So v of s is essentially saying how good is it to be in a particular state, right? So if we go back to our example, like, what's the value of the state? What's the value of the state? What's the value of the state? So let's say we say that the value of the state is 10, the value of the state is 8, this one is 8, this one is, say, 6, and this one is 5, or this one is 4, or whatever. So if you're in this state, right here, this is where your agent is, let's say. Why do we need to know what this value function is? We need to know it because we are actually trying to determine, like, from here, where are we going to move? Should we move in this direction or in this direction? Well, this state is a higher value function. I'm gonna explain later on, like, how we compute this value function and so on. But say that you're given that this state is a value of 5 and this one is a value of 4. So you know that it's better for me to be in this state, so you'll make a move to go into this state, right? And from here you go like, okay, let's say this is a value of say 4 again. Oh, okay, it's better for me to move down there, and here, whether I move here or here, it doesn't make a difference, and finally you reach there. So your value function actually gives you an idea of where you actually want to move based on how good it is to be in a particular state. Okay. So if you understand that, this is how we define VS, right? So how good it is to be in a particular state, right? That's what our value function is. And the next thing we actually need to know is what is policy, right? So we denote a policy by pi, right? Pi of s, right? So what is pi of s, you might ask? Well, this is what action to take in a particular state, right? So this pi of s gives us information of what action are we supposed to take. We denote it as pi of s. So again, in our example here, if we are in this let's say initial state here, we're in the initial state, and we say what is pi of s0, right? And someone say pi of s0 is equals to right. Okay, that means that the policy said if we're in state s0, we should move to the right. And then pi of this a is equals to, maybe if we're here, we want to also move to the right, this should be right. And then pi of and so forth. That's basically like how it's working. Like if we say pi of course b, again, is to move in a certain direction and so forth. This has become too cluttered, so I'll just leave it at this. So that's what pi is. It's just a function telling us what to do in a particular state. So please note the difference between the value function and the policy. The value function just tells us how good it is to be in a particular state, and the policy is a function telling us what action to take in a particular state, right? So if we have an understanding of what these things are, then we are actually going to look at something called v pi of s, right? What is this now, right? That's what you are probably going to ask yourself. Well, v pi of s is essentially saying using policy pi, right? Using this policy, what is the value of state S, right? So if someone gives you a policy, like by saying give you a policy is just telling you that in every state you're supposed to perform a particular action. So someone gives you this function, right? It's in the future video that we're actually going to go through how we estimate this function, but for now let's just say someone gives you this function, and now that you have this function, you are supposed to calculate, right? You're supposed to calculate the value of being in a particular state given this function, right? This is what we call v pi of s, right? So you're given pi, right? And you're trying to find the value of being in each state under the given policy. Okay, that's the idea here. So under the given policy, you're trying to find the value of being in each state. That's what v pi actually ends up being here. So we are going to assume right now that we're given pi and we're trying to find the value of being in each state, and this is what we call the prediction problem, right? This is the prediction problem. This is the prediction problem, also known as policy evaluation, which is the main subject of this lecture, actually. The main subject of this lecture is policy evaluation as such. So let us start on the policy evaluation algorithm. Now for you to understand this, make sure that you've actually gone through our previous lectures, because you'll need to know what transition probabilities are, how they work, and so forth. So let's start again. So what is, again, v pi of s? We've already gone through this. We've been given pi, and we need to estimate the value function of s. So how good it is to be in state s under policy pi, right? Well, this is actually equal to the expectation, right, under policy pi of the return gt given s. So of course, like, you might wonder to yourself, like, what does this actually mean, right? What is this? So we defined the return as the accumulation of discounted rewards. So I'll just rewrite the formula here. RT plus 1 plus gamma RT plus 2 plus gamma squared RT plus 3 and so forth, right? This is how we defined the return. So given this definition for the return, we are actually trying to now say that, well, we don't know what RT plus 1, we don't know what RT plus 3 is, RT plus 3 is, and so forth. So because we don't know where we're going to end up in our series of events. So these R's are essentially random variables. And since they are random variables, we are going to need to take the expectation, right, of these variables. Right? So how good it is to be in a particular state is essentially like, what is the expected reward, what's the expected cumulative reward that we'd get starting from that state. Okay, that's essentially how good it is. So if we start from state S, and then what's the expected reward, that's the value of being in that particular state, essentially. So given that, we can now infer a couple of things here, right? So this is the expectation of GT given S, right? and this is actually equal to the expectation under policy pi of, we can actually divide this into RT plus 1, right, plus gamma multiplied by GT plus 1 given S. Now, why is this the case? Because all of this here, well, if this is RT plus this, if this is GT, then obviously, if GT is RT plus 1 plus gamma times some function, that means if we start from RT plus 2 here, this is actually signifying GT plus 1, right? That's the idea here. So you should convince yourself why this is the case, but I think it should be simple enough to see from here. Okay. So now that we know what all of this is, we go on to the next problem. So we've broken down this equation like that. We can break it down even further by saying this is the expectation under policy pi, the policy that we've been given, of RT plus 1 plus gamma, right, V pi, right, ST plus 1 given S. And why is this the case? Because we said V pi of S is the expectation of GT, right? So how good it is to be in a particular state. So we can actually replace GT with V pi ST. So GT plus 1 can be replaced with V pi ST plus 1 in this expectation. So we can break down this even further now, right, by saying this is actually now we're breaking down the expectation to the summation over all possible actions of pi a given S. I'm going to explain what this actually means, right, times the summation over all S prime comma R of P S prime comma R given S comma A. This is our transition probability. This is transition probability multiplied by R plus gamma V pi of S prime, right? This is actually summation of a S prime, sorry. So, of course, now you're probably wondering, like, how did we actually get to this stage? Like, we actually just broke down this expectation. So let me break down these terms one by one. Okay, let's start with this term here, this term over here. So what this term is saying is summation of pi a given S, right? So if you remember, pi a was actually supposed to be the policy, right, that we take in a given state. Pi S was kind of like what action should we take in a given state. But sometimes this action can be a probability distribution, right? So this is essentially like, okay, this is equal to some action you should take. But if you're now given pi, if you're now given pi a given S, that means A is taken, action A is taken with some probability, right? So if we can take action 1 with a probability of, let me clear this up. Probability of taking action 1 maybe is 0.2, probability of taking action 2 is 0.8, right? This is given that you're in a particular state. So this is actually probability of A1 given S, probability of A2 given S. So this is essentially saying that pi of a given S, the probability of taking an action in a given state. That's what this is, right? So that means that the action that we take in our given state is not always certain. We might take different actions with different probabilities. Right? Now this is the transition probability. You should know what it means. The probability of ending up in some future state S prime, comma R, given that you're in some state S and you take action A. And this is the reward that you get for taking that action, plus gamma times what we have here, which is a value function for being in a future state, right? So I know right now this is most probably not clear to you, and that's perfectly fine. I'm actually going to explain using something that we call a backup diagram, and this should clear all your doubts, and it's a different representation of what this actually means. Of course, you can actually work through in your head right now. You can pause the video and think about why this formula leads us to this position. But right now, I'm going to make it even simpler by looking at this formula using a backup diagram. Okay, so let's do that. Oh, sorry. Okay, so we're going to start with okay, let me go back to our traditional black with a backup diagram, so that you understand. This representation we showed here was for those that are more like into the math and the statistics of how it's actually working, but this diagram should help you visualize actually what's actually going on as such. So let's start with our backup diagram, and we start here, okay, in a state S. Okay, so from this state we can take an action A1 or a different action A2 or another different action A3. I hope you can follow, right? So from given state S, I don't know, S0, we can take actions A1, A2 or A3, right? So we define pi of A given S0 to be the probability that you take a particular action from state S0. So we can have some kind of definition like, okay, the probability of me taking action 1 in state S0 is equals to let's say 0.2. The probability of me taking action 2 in state S0, maybe this is 0.5, and the probability of me taking action 3 in state 0, maybe this is equal to 0.3, right? So we've broken down those probabilities, right? Like, so that's what this pi a given s comma 0 actually means. Okay, so this should help you understand what this term is. Okay, sorry. Now if you take any action, right, you might end up in a new state S1x with some probability. Let's say you take action A1, or maybe you might end up in some other state S1y with another probability. If you went through our previous lecture, you should be able to understand why one action can lead to different states, right? Please see the previous lecture in case this actually confuses you. So what does this actually mean? It actually means that, okay, we have a probability of ending up in state S prime, where S prime can be S1x or S1y, right? Getting some reward R given, right, that we're in some state S and take action A, right? This is what it's. So for simplification, we will abuse this notation a bit and just represent it as S prime given S comma A. So these two, you can just think of them as interchangeable because in most of the times these are associated anyway. So the probability of ending up in some state S prime given S comma A. So these two are interchangeable. Right. So I can either use this one or this one, just depending on things. So what we have here is that the probability of ending up in S1x, right, given that you're in S0 and you take action A1. That's what this line here is representing. The line that you see here, the chain of events that goes up to here, is actually representing this, the probability of ending up in S1x given S0, A0. And the other chain of events, the one we see here, going down there, what this is essentially is the probability of ending up in S1y given that you are in S0 and you take action A1. That's what this is. So we have these two probabilities that are essentially represented by this here. What that means is that you start in S0, right? You take an action A1, right? With some probability, okay? The probability of you taking action A1 given you're in S0 is equals to 0.2. After taking action A1, you're going to get a reward, of course, right? You're going to get a reward R. This is your reward. And after getting this reward, you'll end up in some future state S prime, right? This is something we've gone through in the previous video. So again, it's we're just now representing it using this thing known as a backup diagram, right? So what does this actually mean? Well, we can actually break it down even more back to our formula. So what is the value of being, again, under some policy pi, of ending up of some state S, right? This is kind of what we want to compute. The value of being in S0, essentially. What's the value of being in this state here? That's what we want to know, the value of the state. So the value of this state is essentially equal to the summation over all of the actions, right? All the actions that we can take in the state, right? Because this is again an expectation. So since it's an expectation, we're going to consider this probability and this probability and this probability and sum over all of them, right? So of A given S, which is what we have here, because we might take any of these action, right? That's what this is representing. And then once we take action A, we'll get some reward, right? So we'll get some reward R and end up in the state S prime, right? So plus gamma end up in the state plus gamma, the value of S prime, the future state that we might end up in, okay? So the value of being here in S0 is the reward I get for taking this action plus the value of this state, which I don't know yet, but we're actually going to go through how you actually can know what this value actually is. However, we have iterated that this chain of events happens with a certain probability distribution, right? So this distribution is again given by the summation over s prime comma r of ps prime given s comma a, right? So we might end up in this s1, or we might end up in this s1. Again, another expectation that we're computing here. So that's why we need to multiply the probability of ending up in each of the s primes with the reward that we get plus the value of each of these s primes. Again, this is another way of just arriving at the same formula that we saw here, but with a more visual representation of what is going on in this backup diagram. But what you need to actually understand here, what's most important actually, is that like the way that we arrived here, it might be confusing to you actually at this moment, and that is still fine, because we are actually gonna go through a proper example. Like when we go through this example shown here at the very beginning, as we were doing, as we're writing our programs, you can actually better see like how it's actually working. For now, you don't need to actually get a full understanding of what's happening, but if you did, that's also great. But if not, that's fine, because the example that we're going to show, like the program that you're going to write and so forth, should help you like understand how this algorithm is working, right? So as such, let's move on. Now that we know this is our formula, like the value of being in state as 0 depends on the value of being in state as 1x or as 1y, or rather s prime, right? And this actually causes some kind of problem. Oh, sorry, this should be value of being in state s1. So this causes some kind of problem. We're trying to estimate the value of being in s0 by looking at the value of being in s1, a future state, right? Well, then that means that we kind of have to iterate, right, in order to actually get what these values actually are. And I'm gonna show you what this actually is, maybe from a programming point of view. So what is the value? What is vk, right? Plus 1 of s. Here we're defining what is essentially our update rule. So the value of being in state s at time step k plus 1, right? Well, this is essentially the expectation over pi of rt plus 1 plus gamma vk st plus 1 given st. This is actually essentially the same expectation that we had here. Sorry. That we had over here. We're just representing it using time steps. Okay. This is our update rule, essentially, right here. This is our update rule. Update rule. We can also represent it as summation over a of pi a given s, summation over s prime comma r of probability of s prime given s comma a, our transition probability, r plus gamma vk of s prime. So again, this kind of formulation we have is that the value of vk plus 1 is actually depending on now the value of vk. Okay, so we're looking at the previous value and so forth. So this is what we call the expected update. That's another name for this update rule. Okay. So this is kind of like our update rule for showing this kind of value iteration problem. Policy iteration problem. So now that we've reached this point, right, I should also mention a key point that I'm going to just write down the basic algorithm for solving the policy evaluation problem uh, using this update rule. Uh, so this algorithm, and actually most of the material that I'm covering, is actually in a book by R.L. By Sutton, Introduction to Reinforcement Learning, I think was the name. So if you search for Sutton's book, and you should be able to see this stuff in more detail. I'm just trying to cover and explain the concepts that are actually illustrated in here, and I'm going to add, of course, programming exercises and so forth for this. So let's go through our policy evaluation algorithm, the iterative. So this should be good for the programmers, I guess. Iterative policy evaluation, right? So what was the first thing we assumed? We are actually given the policy, right? Someone gave us this policy and they want us to evaluate this policy. So this is our policy to be evaluated, right? So the first thing we need to do, right, is we need to initialize an array, right? Vs, the value for all the states, right? So Vs is equal to 0 for all S is an element of S, which is our, I'll say capital S. Like this is our state space actually. So this is our state space. So we initialize the values for each state in the beginning to be equal to 0. And after that, we're going to repeat the following, right? So we start by some delta. We initiate it to be equal to 0. This is for convergence properties, but we'll go to it. Now, for each state, S is an element of S, right? What we want to do, right, is to assign V, right? What are we assigning V to? V is equals to Vs, okay? Some V is equals to Vs, the value of that state. And then what is Vs? Well, we know what Vs is. We know the update rule. It's the summation over A of pi A given S times summation over S prime comma R of PS prime comma R given S comma A. Again, this is interchangeable with this in case you forgot. Like this is, we're just saying this is the same thing. And multiply this by R plus gamma times V of what? S prime. Okay. This is essentially our update rule. And we update our V. And this delta is now equal to essentially the maximum between current delta and V minus Vs, right? So what does this mean? Well, when the values stop changing much, right? That's what this is essentially doing. It's just looking like, okay, when the values actually stop changing much, that's when we can say that this algorithm has converged, essentially, right? So this is gonna happen until delta is less than theta. This is until delta is less than theta, some small number, right? So this is essentially, in a nutshell, what iterative policy evaluation is, like the actual algorithm for it. Maybe it's difficult to see it from this kind of view. This is just pseudocode from Sutton's book. But we are actually going to implement this algorithm, of course, ourselves. And when we do, you should have a better understanding, of course, of how it's actually working and so forth. So this concludes our lecture on iterative policy evaluation. I hope it has been informative to you. And in the next lecture, we're going to look at policy improvement. Thank you.